Swayam Prabha. Digital India. Educated India.
Welcome. In the last class, we have been discussing the Brownian motion of a free particle in an external field, and the motivation that I have already given you is that we want to use that to discuss the Brownian motion of polymer chains. We required an external field discussion because when we look at the motion of polymer segments, every bead experiences some spring force due to other neighboring beads, and also it experiences the usual solvent drag and thermal motion of solvent molecules. And therefore, we have first discussed that how can we incorporate an external field into it, and the same idea we are going to use to incorporate the effect of spring force, and using that we can build the model of a polymer chain, the Brownian motion model of a polymer chain, that is known as the Rouse model. So, we will talk about the Rouse model. So, it is actually simply an extension of, or I would say an application of the bead spring model that we already have discussed. So, you have beads connected by springs, and I can represent the positions of beads as say R0, R1, R2 to some say Rn, and now they are in a solution, and so of course they are surrounded by tiny solvent molecules. Although I say tiny, even the beads are not very large themselves, because otherwise the Brownian motion will not really occur or will not be significant in the system. So, then the spring force between the beads is simply given as the minus k, the extension of that particular spring, or we can talk about a spring energy, that is half k extension squared. So, between say two beads, or better still we can say for any bead that is located at Rn, it experiences two spring forces due to the n plus 1th bead and n minus 1th bead, which are located at Rn plus 1 and Rn minus 1. So, if I talk of the spring energy, that is present at Rn for bead n, that is because of the two neighboring beads that we have, that we can write as half of k Rn plus 1 minus Rn squared, that is for the spring right here, and then we have half k Rn minus 1 square, that is for the spring on the left. So, using that we can get the force that is dou u by dou r n, which is now a vector. So, I am taking a derivative with respect to vector, but the rules of differentiation remain same as we normally do for a scalar as well. So, we have minus k of r n minus r n plus 1 minus k of r n minus r n minus 1. They are the two spring force. So, now this becomes minus of k, and then we have actually plus of k, we have r n plus 1 plus r n minus 1 minus twice of r n. So, now we have to be slightly careful for the beads at the end. For the beads right here, there is only one spring coming from R1. So, right here the u is half k R1 minus R naught squared, and so F would be minus k R naught minus R1, and similarly for here we have F is equal to minus k R n minus R n minus 1 due to the bead that is present right here. Okay. So, now we have found the forces because of the springs. All of them are the force only because of spring, and of course, we have other forces in the system. So, let us go back to what we derived in one dimension. We had dx by dt is equal to minus 1 by zeta dou u by dou x plus some VRT, where VR t was equal to FRT by zeta, and VR follows the relations. The mean value is equal to 0, and the autocorrelation is given by this particular relation. Okay. So, if I now extend it in the case of a polymer chain, I have to write separate equation for each of the beads. That is to say that we have to write equations like drn for bead n is equal to minus 1 by zeta, the force acting on that spring. So, then this becomes plus, because minus dou u by dou x is force, and then plus of the VRT. So, now we can write it for all the intermediate beads as one equation, and for the end it has to be a separate equation. So, for n equal to 1 to n minus 1, we have drn by dt is equal to k by zeta with what we have derived. And then for n equal to 0, and n equal to capital N, we have a separate relation. So, for n equal to 0, we have this, and for n equal to capital N, we get this relation. Okay. So, there is one thing we can see here, and that is that if I look at the term right here, this has the form of the second derivative in the finite difference form, and this has a form of first derivative, and this also has a form of the first derivative in the finite difference form. That is to say that if capital N is very large, then as I was doing for the case of a polymer chain, I can approximate the bead spring model as a continuous contour, and then instead of talking about the discrete differences, we can talk about derivatives along the contour and second derivative along the contour and so on. So, if I now approximate the model as a continuous model, which is going from n equal to 0 to n equal to capital N, and R being now a function of the contour variable n, then in that case dou 2 R by dou n square can be approximated by R n plus 1 plus R n minus 1 minus 2 R n. It has to be divided by delta n square, but delta n is equal to 1 in this case, and increases in increments of 1. So, we get this particular relation, and then we can write for the two ends as the first derivatives. So, dou R by dou n is equal to R1 minus R0, again delta n is equal to 1 for n equal to 0, and then dou R, all these are approximations by the way, by dou n for n equal to capital N has to be R n minus 1. This is like a central difference approximation. This is a forward difference, and this is a backward difference. If you are having any trouble understanding this, please read about finite difference method in standard mathematical textbooks. So, I will not go in details here, but you can read in standard textbooks. Okay. So, now if I go back here, the equations I have derived, now I can write them in a continuous notation. So, this equation for example will become drn by dt is equal to k k by zeta dou 2 r, this will be careful here, it has to be dr by dt, because now r is a continuous variable, by dou n square plus Vr of t and then I can also modify the two equations at the boundaries again using those derivatives. There is something else that I can use here and that is what I will explain in a moment. Instead of looking at, so of course I can write this equation for example as dr0 by dt is like k by zeta dou r by dou n plus Vrt, where this derivative is computed at n equal to 0. Similarly, this equation, this is by the way, you have to be slightly careful here in how I am writing the dou's. So, now r is a continuous function in n and t, so this becomes dou r by dou t. So, now r becomes a function in n t, so this also has to be dou. So, we can always do this, but now you see that this problem becomes somewhat complicated, because if this is my partial differential equation and these are my boundary conditions, then these boundary conditions are in somewhat complicated form and it is not really easy to solve, because the boundary conditions itself are ordinary differential equation. So, we will do a trick here, and the trick is that if I look at these two ends, they are essentially free ends, and since they are free, there is like nothing before them. So, the any gradient that is present there should vanish at the free end that we have, that is there nothing before this, nothing after that. If it was like clamped on say two walls, then this is no longer true, then the gradients will be present at the boundaries, but in this case the gradients has to vanish at the end, because it is a free end. So, what we assume is then dou r by dou n is equal to 0 at n equal to 0 and capital N. That is because the ends are free, there is no polymer chain. If I go further from n equal to 0, nothing there at n equal to -1, similarly nothing there for n equal to n plus 1. So, there the gradient must has to vanish. Okay. So, now I have the full statement of the Rouse model. In continuous approximation, and that is we have a partial differential equation for r and t, where what we are now solving is for the positions as a function of n and t, n being a contour variable running from n equal to 0 to n equal to capital N, and the PDE we have something like this. So, of course, if I look closely, then the random force was of course different for different beads in the system, and therefore the random force should also be a function of n, because since we have replaced the r n's by a continuous variable r, continuous function r, which is a function of n and t, the random forces also differ for every bead. So, they also have to be a function along the contour. So, they also have to be changing with n and t, and therefore, although not clearly stated earlier, this has to be Vr as a function of n and t. Okay. So, for every value of n, we have to find a new random function, or it is a continuous random function that would change its value as n is changing. Okay. With the boundary condition dou r by dou n equal to 0 at n equal to 0 and capital N, this becomes the statement of the Rouse model. Now, it turns out that this is a second order partial differential equation, and it is somewhat difficult to solve. So, in the next class what I would discuss is we can write this equation equivalently in terms of a series of ordinary differential equations, and those ordinary equations are easier to solve, and then we can get solution in terms of what is known as Rouse modes, which I will elaborate in the next lecture. So, we are going towards what is known as a normalized coordinate or a Rouse mode, and we want to find solution in terms of them, and that is where we will take the discussion in the next class. So, I want to stop here. Thank you.